In this video, we're going to take a look at another optimization problem. A straight section of railroad track crosses two highways 400 meters and 600 meters from an intersection. Find the dimensions of the largest rectangular lot that can be laid out in the triangle formed by the railroad and the highways. So the first thing we're going to do is we're going to draw a diagram. So we have, in this case, our two highways. So this is one highway, this is another highway. And this is the intersection of the two highways. Now running across is a railroad track. Okay, and so it crosses the two highways. And so it crosses at 400 meters from the intersection and 600 meters from the intersection of the two highways. And what we're trying to find are the dimensions of the largest rectangular lot that can be laid out in the triangle. Okay, so we have this triangle here, and here is the rectangular lot that's going to be laid out. So for the rectangle, we're going to let x represent the length of the rectangle. We're going to let y represent the width of the rectangle. Okay, and what you notice here is that this point here is actually x and y. Okay, so the point on this line is x and y because it's determined by the length and the width of this rectangle. Okay, and so the intersection is located at 0, 0, which is the origin. So if we consider this to be a Cartesian plane, okay, this would be 0. Okay, and so this is 600 and 400. Okay. Now, what we could also have instead, maybe the rectangle doesn't actually look like this. Maybe the maximum area would be achieved if it actually looked like this. So we don't know yet what it's going to look like. Okay, so this is just another scenario. So maybe it actually looks like this. But still, this point here is going to be, the x-coordinate of it is going to be x, because this is x. And the y-coordinate of it is going to be y, because this length is y. Okay? We're going to let A represent the area of the rectangle. And so we have this equation for the area. Okay, so area is equal to x times y, so length times width. Now what we're going to determine is the equation for this line. Okay, because the area of this rectangle is dependent on x and y. Okay, and this edge of the rectangle is always going to be on this line. Okay, and so the y coordinate of this point will depend on the x coordinate. So the width of this rectangle, which is represented by y, is going to be dependent on the length of the rectangle, represented by x. And so we start with a general equation. So general equation for a line. So y equals mx plus b. And the first thing we're going to do is find the slope of the line. So in this case, calculating the slope. So the slope is equal to y2 minus y1 divided by x2 minus x1. And in this case, this is our second point. Okay, so 600 and 0 is our second point. And our first point is 0 and 400. Okay, so we're doing 0, take away 400, divided by 600 minus 0. And we get negative 2 over 3. So when we Simplify this, we get negative 400 over 600, and that simplifies to negative 2 over 3. So now, since we know our y-intercept, we know the b value is 400, we can write our equation for the line representing the railroad track. So we have y equals negative 2 over 3x plus 400. So now, we're going to write the area equation in terms of x. Okay, so we know that the y here depends on the x. Okay, and so the area of this rectangle is really dependent on this line. Okay, because it has to fit underneath this line, and this point of it is always attached to the line. So we're going to have a is equal to x times negative 2 over 3x plus 400. So we're replacing the y here with this expression here. And so what we get is we're going to get a quadratic equation. Okay, but what we need to do is we need to find the x coordinate of the vertex of the parabola. Okay, that's going to represent the length that will give us a maximum area. And so this is our equation. So if we expand this, right, if we distribute x in, we end up with this quadratic equation. So now we're going to complete the square in order to find the x coordinate of the vertex, so the length. Okay, so the first thing we're going to do is we're going to factor out negative 2 over 3, and then we're going to take half of this value, so half of negative 600, and then we're going to square that. So half of negative 600 is negative 300. We're going to square that. We're going to get 90,000. So we're going to add 90,000 inside the bracket, and we're going to subtract 90,000 inside the bracket. So next we're going to take the negative 90,000 out of the bracket, and when we take it out of the bracket, we're going to multiply it by the negative 2 over 3 outside, and we're going to get 60,000. And the last step is now to change this into a perfect square. So we're going to factor this to get x minus 300 inside the bracket, and that bracket is going to be squared. So now we have the quadratic equation in vertex form, and from this we can conclude that the x coordinate of the vertex is 300, and the maximum area is 60,000. So we have the length, so the length is 300. So now all we have to do is find the width. And in order to find the width, we're just going to use this equation. Okay, so the equation for the line. We're going to substitute 300 into x. And from that, we get that the width is equal to 200. Okay, so our rectangle is going to look more like this than this. So the length is going to be 300 and the width is going to be 200. So therefore, the dimensions of the largest rectangular lot that can be laid out are 300 meters by 200 meters. So this is an optimization problem that doesn't require us to use calculus. Okay, so all we have to do here is just set up a quadratic equation and then find the vertex of the quadratic equation. So find the maximum point or maximum value of the quadratic equation. Okay, thank you for watching.